continue on with learning target 13A. Our next big idea we're going to talk about is what is sine, cosine, and tangent for any angle on the unit circle. So before we can get down to defining what sine, cosine, and tangent for, we have to correlate this back to the unit circle that we have. So I have an XY plane drawn on here. We would have our unit circle going all the way around, and we're taking this terminal side of our angle that's going to end somewhere in the first quadrant for this example and for the definition, and we're looking at this angle theta. So for any angle on the unit circle, I can create a right triangle from it by taking the end of my ray and dropping a line down to the x-axis that is perpendicular to it, and this will form a 90-degree angle here. Now the reason we want to do this is so that we can relate our unit circle to our special right triangles, the 45-45-90 triangle and the 30-60-90 triangle. By creating this right angle that we have, we end up with a horizontal leg, which I'm going to call that distance x since it's a horizontal distance, and this vertical side of the triangle, which I'm going to call y since it's a vertical distance. And then of course we have our hypotenuse here of our triangle, which is also the radius of our circle. But since we are dealing with the unit circle, then this radius for us is going to be equal to the number 1 since we are on the unit circle. From here, we can actually define sine, cosine, and tangent from these. Now, I'm going to guess that based off of the survey I gave you guys, a lot of you guys are familiar with the phrase SOHCAHTOA from geometry. And we're going to use that just like you guys did in geometry for defining sine, cosine, and tangent for their definitions. So, sine of theta, which is written as sin parentheses of theta, where theta will be our angle, is defined to be opposite over hypotenuse, so it's the SO in SOHCAHTOA. Opposite over hypotenuse is helpful, but we also need to know how this correlates back to our unit circle. So when I look at this angle theta here, it is opposite, the side opposite that angle will be our y value. So another name for our opposite side is going to be y, and then our hypotenuse is our r value. Again, since we're on the unit circle though, this r value is going to be equal to 1. So this is the same thing as just saying that sine of y is going to be equal, sine of theta is going to be equal to y. Cosine of theta is defined similarly. It's the c part in SOHCAHTOA, and its cosine is defined to be adjacent over hypotenuse. If I go to our right triangle, our adjacent side here is the x value, and then our hypotenuse is r. Again, since our r value is 1, cosine of theta is the same thing as x then, or the x side of that triangle. Tangent is going to be our last trig value that we're going to look at, and tangent of theta is defined to be opposite over adjacent, so it's the TOA part of SOHCAHTOA. So our opposite side of our triangle here is the y value, our adjacent side is the x value. These are going to be 3 definitions that we're going to have down in order to be able to find sine, cosine, or tangent of any angle on our unit circle. The SOHCAHTOA will be helpful, so that's an acronym that you can help remember that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. We also do want to relate them back to our right triangle here, because there's going to be some times where I can't actually draw a triangle, and that's going to happen when I have an angle that is on an axis. So if I'm on an axis and I'm up here at the top of the y-axis, I can go and draw a perpendicular line down, but I'm not going to create a triangle shape out of that. And because of this reasoning, the definitions for sine of theta being equal to y, cosine of theta being equal to x, and tangent of theta being y over x, that's where those are going to come in handy, and we'll see some examples of those at the end. Again, I want to remind you guys of what our goal is for this learning target. It's to be able to quickly find sine, cosine, and tangent for any angle on the unit circle without the use of any notes or a calculator. For now, since we're starting out and for the rest of this semester, you guys will be expected to show all the work. What I mean by that is I want to see you drawing out the triangle like I'll be doing in the examples today, labeling our reference triangle, and then finding sine, cosine, and tangent of those values. Okay, make sure when you're drawing these out that we're not just drawing a 30, 60, 90 or a 45, 45, 90 triangle, but we're actually relating this back to the coordinate plane. So each one of our drawings should start with our x and our y axis and identifying where our angle is on the unit circle. Now, for us to do this, if I go back actually to this example where I drew this triangle, this worked well because I was in quadrant 1. Now, if I have a triangle out here in quadrant 2, let's say I have the terminal side of this, let's make it somewhere over here, whatever this angle would be, then theta would actually be that angle right there. To get our right triangle, I would drop a line perpendicular to the x-axis, and I would get this right triangle here. Well, I'm trying to figure out what's going on with theta, but theta's outside my triangle. This is why we're going to have to find what we call a reference angle, and this reference angle we're going to call theta prime will be the angle that is inside our right triangle for something in quadrant 2. Now I'm going to get similar things that happen in quadrant 3 and quadrant 4 because theta is not actually going to be our reference angle, and we'll talk through those. Okay? So for our reference angles, remember theta prime is going to be the reference angle, and that angle, so that value for theta prime is either going to be 30, 45, or 60, so that we have one of our special right triangles, and we're going to use that to get the sides of the triangle. Now in quadrant 1, they're going to be equal because the angle is already inside the right triangle that we would draw. So if I draw our right triangle here for reference, remember we drop down to the x-axis, my angle is already the exact angle that I was given in the problem. But in quadrant 2, like we were looking at earlier, when I take this and I draw my perpendicular line down to the x-axis, the angle that we started with, this theta angle, is not actually inside this triangle. So this is where this concept of a reference angle is going to come in handy. So here in quadrant 2, to find our reference angle, it's the extra stuff that would get us all the way to 180 degrees. So remember, 180 degrees is over here on the negative x-axis, 0 is on the positive x-axis, and if theta is the angle up until that point, theta prime is the difference between 180 minus my original angle. So to get my reference angle in quadrant 2, we're going to use this equation that 100 theta prime, so our reference angle, is equal to 180 minus our original angle here. Now in quadrant 3 and in quadrant 4, we're going to get something similar. In quadrant 3, if I have an angle all the way over here in the third quadrant, for me to get my right triangle here, remember I go back to the x-axis to get that right angle. So my reference angle is going to be the angle that's inside this triangle, which is this theta prime value. Well, theta that I originally started with, my original angle, is kind of incorporated into theta prime, but theta prime is a much smaller value. So my original angle goes all the way to 180, and then it goes a little bit past. Well, I just want to know what the little bit past 180 is, so my reference angle this time will be theta minus the 180 degrees that we get. In quadrant 4, we're trying to figure out what is the extra stuff. So I've taken this angle and I've wrapped almost all the way around to where I started. To get my right triangle here, I'll go to the end of my ray, drop it back to the x-axis to create my right triangle. So theta prime is the extra stuff that I didn't use to get all the way back to 360 degrees. So remember, when I start here at 0 and I rotate all the way around, 0 and 360 degrees are coterminal to each other. So my reference angle this time will be 360 degrees, so the entire one revolution of the entire circle minus my original angle, so I'll get left with the extra stuff that is inside my right triangle. Now, I've said it once before, but I just want to make sure that we caught it. Our reference angle is going to be a value that will either be equal to 30, 45, or 60 degrees. So each one of these reference angles, since they're inside the triangle, is going to be an acute value, so it needs to be less than 90 degrees. So my three values that we have that are less than 90 degrees are 30, 45, and 60. Okay, we're going to do an example in each one of these quadrants, starting with an example in quadrant 1, and then we're going to move on to 2, so we'll really be able to see each one of these reference angles in action through an example. Let's look at our first guy. So our instructions say draw and label a reference triangle for the given angle theta. And again, I'm reminding you to make sure to drop the leg of your triangle back to the x-axis, not to the y-axis. Then we'll find our exact values for sine, cosine, and tangent. And the first angle we're going to do is 30 degrees. So on this graph, remember I've got quadrant 1, 2, 3, and 4. All of our angles start on the positive x-axis, which is 0 degrees. 30 degrees is going to fall in quadrant 1, since 90 degrees is up here, 180 is over here, and 270 is down here. It's helpful when you're first starting out with these problems to kind of label the axis with the angle value so that you have an idea of which quadrant you're working in. In each quadrant, we have a low angle, the halfway angle, and the high angle. 30 degrees is the lowest value that we have, so our 30-degree angle somewhere around there. Now, I need to get my reference triangle on here. So I've drawn 30 degrees, and 30 degrees is this acute angle that is inside my triangle, but I don't quite have a triangle yet right now. I just have a sector. So to get my triangle, I go to where it intersects my unit circle, and I drop down, and I get that perpendicular line right there. I already know that the hypotenuse is 1 since I'm on the unit circle. The last thing I need to figure out is what is this side of the triangle and what is that side of the triangle going to be. This is where our two special right-hand triangles are going to come into play. So off on the right side over here, I'm going to kind of draw them for reference. So the first one we have is our 45, 45, 90. So remember, I have the 45, my right angle, and the 45. Now in a 45, 45, 90 triangle, what is the length of both sides of the two missing legs? Why don't you guys pause the video and fill in the rest of this triangle. So in a 45, 45, 90 triangle, both legs have a value of root 2 over 2. Since both angles are equal, both sides are equal. And now in our other special right-hand triangle, that was our 60 to 30, 60, 90. So if I draw 60 degrees down here, then I have my little 30-degree angle up there, and I'll draw my right angle. Again, we know our hypotenuse is 1. Why don't you guys pause the video again and fill out the rest of this triangle. Now in a 30, 60, 90 triangle, I have my short side of my triangle, which is always equal to 1/2, and that will always be opposite 30 degrees. And then the side opposite 60 is our root 3 over 2. Okay, using these triangles, I can help answer the question of what are these missing sides. Well, since I'm dealing with 30 degrees, I'm going to be looking at this bottom triangle down here. Now let's start with the side opposite 30 degrees. So in our reference triangle over here, 30 degrees is across from the 1/2, which means over here, if my 30 degrees is attached to the origin, then across from that value is going to be a side of my triangle with a value equal to 1/2. Now the other side of my triangle, which is my long side, will be this horizontal distance, which is adjacent 30 degrees. So adjacent to the 30 degrees here is the root 3 over 2. This has now completed kind of our step A. We've drawn the triangle, we've labeled all three sides, and we have our reference angle in play. The next thing I have to do is figure out, well, what is sine, cosine, and tangent of each one of these? So let's start with sine of 30 degrees. Well, this is where our SOHCAHTOA phrase is going to come in handy. So let's write it out up here so we have it for reference. Now we know from this phrase that sine is opposite over hypotenuse. So when I go back to my angle, I'm figuring out what is sine of 30. So I'm taking it in reference to the 30-degree angle down here. Opposite 30 degrees is 1/2. So sine of 30 will be 1/2 over the hypotenuse here is 1, so technically over 1, but dividing by 1 isn't going to change anything. So sine of 30 is equal to 1/2 then. I can do something similar for cosine. So we'll find cosine of 30 degrees. Remember, cosine of 30 degrees cosine is equal to adjacent over hypotenuse. So I'm going back to my 30-degree angle. Adjacent to this will be our root 3 over 2, so this horizontal distance. So cosine of 30 degrees will be equal to root 3 over 2 all over, well, our hypotenuse is 1, so all over 1, but again, dividing by 1 is not going to affect anything. So we get cosine of 30 to be root 3 over 2. Now the last one we have to figure out is tangent, and this is going to be a little bit more in terms of simplification since I'm no longer involving my hypotenuse. So tangent, by definition, is opposite over adjacent. When I look at my triangle, opposite 30 degrees is the 1/2, so I get 1/2 over the adjacent side is the root 3 over 2. Now this I need to simplify because I don't want to have messy fractions within fractions. I want to be able to really tell what that value is. Well, when I have a fraction divided by another fraction, that's the same as multiplying by the reciprocal of the denominator. So I'm going to keep the 1/2 and multiply instead by the reciprocal of the denominator, which will be 2 over root 3. Now from here, the 2's will cancel, and I end up with 1 over root 3, which looks a lot more simplified. But because we want this to look nice, I want to rationalize it so I don't have a radical in the denominator. And the way we rationalize is to multiply by the square root of 3 over the square root of 3. Now the reason I'm multiplying by root 3 over itself is because technically this is equal to the number 1. So if I can multiply by a fancy version of the number 1 here, I'm not actually changing this expression. If I were to multiply by any other number besides something that's equivalent to the number 1, I would actually be changing my answer there, and that would no longer be valid. The reason I did root 3 on both of them is because down here my goal is to get rid of the radicals in the denominator, and root 3 times root 3 is equal to the square root of 9, and the square root of 9 is equal to 3 then. So on top I get 1 times root 3, which is root 3, and then on the bottom that simplifies down to be 3. So my final answer here for tangent of 30 degrees is root 3 over 3. So here's our first example of something in the first quadrant and what will happen there. One thing I do want to point out is that right now all 3 of these values gave us positive answers. And the reason that happened is not maybe what you think. So as we go on to our next example, we're going to actually pick up some negative signs, which sounds a little bizarre because we're talking about the sides of a triangle. But what we have to remember is that we're ultimately on a coordinate plane here, and it matters how I move on a coordinate plane. Remember in quadrant 1, if I move to the right, I'm getting a positive value, and if I move up, I'm also getting a positive value. But if I were to be in quadrant 2, and I move to the left, then that x value is now negative, and if I move up, the y would still be positive though. Versus in quadrant 3, if I go left and I go down, now both my x and my y are going to be negative. And in quadrant 4, if I go right, the x is positive, but if I go down, then the y is going to be negative. And what that's going to end up producing is that we are going to get some of our trig values that actually give us negative answers. Okay, let's check our first example that is outside of quadrant 1. So the first thing I'm going to do is I need to figure out where is 120 degrees, so I'm going to go back to labeling this. 0's on the positive x, I have 90 up top, 180 on the left side, and 270 way down here. What that helps me figure out is 120 is in between 90 and 180, so what that tells me is 120 is somewhere in quadrant 2. Now in every quadrant I have my low angle, my middle angle, and my higher angle. Now to get from 90 to 120, I'd be moving 30 degrees, so 120 is going to be the highest angle up there. So it's going to be my high portion of this angle. I'm going to draw a quite little steep line there. Now to get my right triangle from here, I need to go from where the ray intersects the unit circle and drop the side of my triangle down to the x-axis to create that right angle. Now 120 degrees is this value that's outside my triangle right now. This is why we need that reference angle concept. So the first thing I want to figure out is, well, what's this angle that's actually inside my triangle? So let's scroll back up to our reference angles and let's look at this general case that I have. So if I have an angle in quadrant 2, to get my reference angle, which is my theta prime, it's going to be 180 minus my original angle. So let's go back down here. I need to figure out what is my theta prime value. So my reference angle over here, which is my theta prime, is going to be equal to 180 minus 120, which tells me that my reference angle is 60 degrees. Which means this angle down here that's attached to the origin and inside the triangle is going to be 60 degrees. So I'm going to try to label it from the side here, but this angle right there that we're looking at is our 60 degree angle. So it's this one that I've kind of colored completely in purple. It's attached to the origin and inside that triangle. What that tells me then is I'm looking at a 30, 60, 90 triangle. Now it's different than example 1 because in example 1, the angle we were looking at was 30 degrees that was attached to the origin. Now we're looking at an angle that's 60 degrees. What that tells me then is the side opposite 60 is always root 3 over 2. So my vertical side now is root 3 over 2. And my horizontal side, which is the short side of this triangle, is the 1/2 value. But as I was saying a couple minutes ago, because I'm in quadrant 2, I have to think about how I'm moving on this coordinate plane. To get to this horizontal side, I had to move to the left from the origin, which means this is actually a negative 1/2 value. Now, I know that that sounds really strange to say that the side of a triangle is negative 1/2, and I'm not saying that. This reference triangle that I'm using does have a side that is 1/2. The reason I'm taking the x value to be negative is because I moved to the left. And then the vertical side, though, still stays positive because it is still moving in the upwards direction, which we have defined to be positive. And of course, our hypotenuse is equal to 1. So we've now labeled all the sides of our triangle, and we're going to find sine of 120, cosine of 120, and tangent of 120. So let's start with sine of 120 degrees. Now I know it seems kind of weird because 120 is not even inside my triangle right now, but the reference triangle will give me the values for sine of 120 degrees and cosine and tangent. That's the beauty of using a reference triangle. So sine is opposite over hypotenuse. So if I look back at my reference angle, I'm trying to figure out what is opposite the 60 degrees. Well, opposite the 60 degrees is the root 3 over 2. So sine of theta is sine of 120 degrees is going to be equal to root 3 over 2, technically over 1, but that's not going to change it. So I get sine of 120 is equal to root 3 over 2. Why don't you guys do cosine of 120 on your own right now, and then let's check it. Okay, remember cosine is adjacent over hypotenuse, so I'm looking at my reference angle. So adjacent to my reference angle is this horizontal side, which is equal to negative 1/2. So cosine of 120 is negative 1/2 over my hypotenuse, but dividing by 1 won't change anything. Okay, let's do our last angle, which will be tangent of 120. Again, I'm going to have you guys pause the video and try to figure out what tangent of 120 is on your own first, and make sure you simplify all the way. So for tangent of 120, in our SOHCAHTOA phrase, tangent is opposite over adjacent. So from 60 degrees, opposite that would be root 3 over 2. So I'll get root 3 over 2 all over. Our adjacent side is going to be negative 1/2. So when I simplify this, I'll do the same thing I did before. So I'm going to multiply by the reciprocal of the denominator. So I keep the numerator the same. I'm multiplying by now 2 over negative 1. Conveniently, the 2's are canceling, and I end up with negative root 3. So I can bring the negative sign up to the numerator and write the whole thing as just a negative square root of 3. Okay, so we've seen our first example now of an angle that is not in quadrant 1, and we had to remember that we had to create this reference triangle, and the way we got our reference angle was going back, that's back to our last video, going back and using the relationship that the angle theta has with the 180 degrees, and we're trying to find that extra stuff, which would be the 180 minus the original angle. So in this example, when we did it, it was 180 minus the 120. So our reference angle that we have down here is the 60-degree angle. Now the next one we're going to do is going to move to another quadrant as well. So this time we have theta equals 225 degrees. Now let's think about where that would be. Well, 0's on the right side, 90 degrees is up top, 180 is on the left, and 270 is down here on the bottom. Well, 225 degrees is somewhere in between 180 and 270. Now, in each quadrant, remember I have the low angle, the middle angle, and the high angle. Now, if I were to subtract this, to get from 180 to 225, I would need to add 45, which means that 225 is the halfway angle right there, and that will be 225 degrees. And that's the angle going all the way from 0 all the way around to this terminal side. Now again, I need to be able to figure out what my reference angle is, because my right triangle here is going to go from where 225, the ray of the terminal side of 225 intersects my unit circle. I'm going back to the x-axis to get my right angle there. My reference angle is this extra stuff that is the value between 180 and 225. So to get my reference angle this time, it is going to be equal to the 225, my original angle, minus 180, and that gives me a reference angle of 45 degrees. From here, we can then label the sides of our triangle because we know our reference angle is 45. So the 45 is this angle that is right in there. Now, because I'm on the unit circle, I know my hypotenuse is 1. Now, this is a 45, 45, 90 triangle, which we haven't done an example with, but we know from our special right-hand triangles that both sides, both legs of a 45, 45, 90 are equal to root 2 over 2. So both of these sides are equivalent to root 2 over 2, but I have to think about how I moved on this. So I went to the left, which means this is a negative root 2 over 2 value, and I also went down, which means this is also a negative root 2 over 2 value. Now from here that I have everything labeled, I can go ahead and find sine, cosine, and tangent for these. So let's start with sine of 225 degrees. Well, we remember from SOHCAHTOA, so if we have our acronym up here for us to reference, sine is opposite over hypotenuse. So when I go back to my reference angle, my opposite side of that would be the one that's across from it. So the negative root 2 over 2, the vertical one. So sine of 225 is going to be equal to negative root 2 over 2. Technically over 1, but that's not going to change anything. Cosine of 225 degrees is going to be equal to adjacent over hypotenuse. So adjacent to our reference angle here would be negative root 2 over 2, and that would be the x value. So cosine of 225 degrees is equal to negative root 2 over 2 as well. So in a 45, 45, 90 triangle, we're going to get sine and cosine some of the times that are equivalent to each other. And the reason being is that both the horizontal and vertical distance are the same in those triangles. What's going to change is sometimes one will be positive, one will be negative, or maybe both negative, like in this case, or maybe sometimes both positive. Now, our last angle trig value we're trying to find is what is tangent of 225 degrees. Tangent is opposite over adjacent, so our opposite side is the vertical negative root 2 over 2. So I get negative root 2 over 2 over my adjacent side is the horizontal one that is negative root 2 over 2. Well, I can simplify this down really nicely. When I have a number over itself, that's always going to be equal to 1, and it's going to be positive because I have a negative divided by a negative. Now, if you don't believe me with that, we can write that out and multiply here by the reciprocal, and what ends up happening is the 2's cancel, and so do the root 2's, and the negative times a negative makes it a positive. Okay, we've got one more example. You can probably guess it's going to be in quadrant 4. So let's look at what happens if I have theta being 330 degrees. Well, I know 0's here, 90's up at the top, 180's on the left side, and 270 is down here. And if I were to keep going, 360 would be coterminal to 0. So 330 is somewhere here in quadrant 4 because it's bigger than 270 but less than 360. What I need to figure out is it going to be the low angle, the high angle, or the middle angle from there? Well, if we think about this, to go from 270, and if I keep going, if I only go 30 degrees, so I'm only at 300, so I need to go a total of 60 degrees from 270. So 330 is my little low angle down here. It's the closest one to 360 degrees that I have. Now, the next thing we're going to work at is I need to create my right triangle. So remember, from the end of your terminal side, go back to the x-axis, and I get that right angle right there. The next thing I need is, well, what's my reference angle? Because technically 330 is this whole portion right there that's turning almost all the way around the circle. Well, in this case, my reference angle, if we go back up and flip back to this page, when I'm in quadrant 4, my reference angle, which is theta prime, is going to be 360 minus my original angle. So going back to this problem then, to get my reference angle, theta prime will be 360 minus my original angle, so theta prime is equal to 30 degrees. And hopefully that's making some sense, because to get from 330 to 360, I would have to move 30 degrees. So my reference angle down here, and I'm going to try to write it, is that 30 degrees inside that triangle right there. Well, because this is 30 degrees, I know I'm on a 30, 60, 90 triangle. The side opposite 30 degrees we can figure out, and we can also figure out the adjacent side. So right now I want you guys to pause the video and finish labeling off the rest of this triangle. First, label what you think this vertical distance is, then label what you think the horizontal distance is. Okay, let's start with this vertical distance. So opposite 30 degrees is always the short side, which is a 1/2 value. But because I'm going down, this is going to be a -1/2. My adjacent side, or my long side of my 30, 60, 90 is going to be the √3/2 value, because it's next to the 30. That will stay as a positive since I moved to the right to get that distance. Now that we have it labeled, well, don't forget our hypotenuse. Our hypotenuse is 1. So now that we have it all labeled, let's go ahead and find sine, cosine, and tangent. Now I want you guys to pause the video and do all 3 of these on your own first, and let's see what you get and check it. So let's do our first one. So sine of 330 degrees. Well, sine from SOHCAHTOA is opposite over hypotenuse, so my opposite side is the -1/2 over my hypotenuse is 1, so sine of 330 is going to be equal to -1/2. Now if we check cosine of 330, there we go, 330, not 33. Cosine is the adjacent side, so if I'm at my reference angle of 30 degrees, the adjacent side is the √3/2 over my hypotenuse of 1, so √3/2 then. Now tangent, as we've noticed, is the one that requires some more work sometimes, just because we have to simplify. Whoops, hold on. Crazy pen. So for us, tangent of 330 might just take a little bit more work to simplify, but finding it, all I need is this triangle label. So using my reference angle, tangent is opposite over adjacent, so opposite is the -1/2, so I get -1/2 over the adjacent side is √3/2. Now from here, we've seen something similar to this before. It was actually almost identical to what we did in the first example. The difference here is that we have this negative sign on our opposite side now that we have to worry about. So again, I'm going to multiply by the reciprocal of the denominator. So I'm going to multiply by 2 over √3. The -1/2 didn't change. The 2's will cancel, so I get -1 over √3. Again, I want to rationalize it, so to get rid of the √3 in the denominator, I would need to multiply it by √3. But to keep the problem fair, whatever I do to the top, I've got to do to the bottom. So I'm technically only multiplying by the number 1. And I end up getting a negative, because don't forget this negative sign in front, root 3 all over 3 then, for a tangent of 330 degrees. Okay, our next couple examples we're going to look at is, well, what happens if I get one of the angles that's on an axis? And this is where those definitions of the x, the y, and the r are going to come into play from the beginning. So let's scroll back up and kind of review those again. So up here on my original triangle that I have, let me erase some of the extra stuff so that we can just pay attention to the original. So on this original triangle that we have up here, when I was looking at this angle, now yes, we called this the adjacent side, this horizontal distance, but I can also call it x because it represents how far I moved across the x-axis. Likewise, this vertical distance, which is our opposite side, I can call y because it represents how far up, or if it's going down, how far down I moved. And this concept of the x and the y is going to be helpful when I'm on an axis, because when I'm on an axis, we're going to see that I can't actually draw a right triangle to be able to reference. I'm not looking at a 30, 60, 90, and I'm not looking at a 45, 45, 90. Instead, I'm going to pay attention to what the coordinate pair is at that point. So let's scroll back down. The other thing we're going to want to keep in mind is the definition. So on the side over here, I'm going to rewrite them out. So sine of theta was equal to opposite over hypotenuse, but that is the same thing as y over r. Cosine of theta is equal to adjacent over hypotenuse, but that would be the same thing as x over r. And tangent of theta is equal to opposite over adjacent, which would be y over x. And we're going to use these parts of the definitions to help us answer these. Well, 270 degrees. Well, I'm going to start by labeling my axes. So I start at 0. Halfway around would be 180. Half of that would be 90 up at the top. And 270 is actually this angle down here on the negative y-axis. Now, if I were to draw a triangle for this, I would go back to the x-axis, but then I just get this straight line. One thing I know for sure is that my radius is equal to 1 because I'm on a unit circle. The other thing I know is that this represents a coordinate pair, that point. It has an x, comma, a y value. Well, let's think about this. To get from the origin down to this point, my x value would be 0 because I didn't move right and I didn't move left. So it would be 0, comma, now the y value, to get down here, I moved a negative distance, so it's going to be negative something, and the distance I moved is actually the radius of my circle. So I moved a distance down that is equal to -1. Now I know I keep saying distance and I'm saying the distance is negative, but that is not what I'm trying to imply. On the coordinate plane, I moved this unit of 1 down, but because I'm moving down, we label that as a -1 value that we have. This coordinate pair, plus remembering the fact that our radius is always equal to 1 since I'm on the unit circle, is going to help us figure out what sine, cosine, and tangent are then. So let's start with sine of 270. So by definition, sine was y over r because it's the opposite. So my y value here is -1 over my r value is 1. So -1 over 1 simplifies just to be -1. So sine of 270 is actually equal to -1. Let's do the same thing for cosine. Cosine of 270 degrees, well, cosine was adjacent over hypotenuse, which is the x over the r. So if I look at my x coordinate here, I'm at 0 over my r value is 1. Well, 0 over 1, remember, since we're not in the classroom right now, I think we need to go back to these two signs that were at my door always. The question at my door, let me put them side by side like they usually are. So remember the two signs I have hanging over my door. It says divide by 0. You guys reference this a lot of the time during the year. I have the one that says okay, and then I have the one that says no. And we're going to use this in a little bit. So the question is, can I divide by 0? No, I cannot divide by 0. That's the case where I have a non-zero number over 0. This would give me something that is undefined. When it's okay is when the 0 is on top, and 0 over a non-zero number will always be equal to 0. So 0 over 1 is going to be 0, which tells me that cosine of 270 is 0. Now the last one we have to do is tangent of 270 degrees. Tangent is, remember, opposite over adjacent, or y over x. Our y value here is -1 over our x value is 0. What happens when I go -1 over 0? That's a big no that I can't do, so I get this value to be undefined. Oh, crazy pen. Sorry, guys. Undefined. So this is actually the first time where we tried to find a trig value of an angle and I didn't get an answer out. So there are actually values, and we're going to end up looking at the graphs of sine, cosine, and tangent in a couple learning targets from now. And what we're going to notice is that there's certain values that I can't find certain trig functions for. And here's our first example. I can't take tangent of every single number. It's not actually going to be possible. What that means then for us when we look at the graph is something's going to happen on the graph then if I were to look at this at 270 degrees. And we'll see that as we move on to those units later. Okay, let's look at the next one. So 360 degrees is our angle this time. I'm going to go ahead and label them. I would start at 0, 90 is up at the top, 180 is on the left side, 270 is down here. Well, 360 meant I went all the way back around. 360 is actually the same thing as 0 because they are coterminal to each other. I'm going to let you guys in on a little secret right now. When you have angles that are coterminal to each other, since they're at the same point on the unit circle, sine, cosine, and tangent of both 0 and of 360 are going to give me the same answer because 0 and 360 are coterminal. And that will happen anytime we have coterminal angles. So although we can find sine, cosine, tangent for anything on the unit circle, once I start wrapping around multiple times again, I'm just going to get the same values for sine, cosine, and tangent because the angles I'm inputting are coterminal then. So you guys are going to start to notice a lot of patterns repeat as you go through your exit ticket. So 360, positive x-axis. Now, if I were to try to draw a triangle, I'd have to go to the x-axis, which I'm already on. So I can't draw a triangle here. Instead, this is where I have to figure out what is this coordinate pair. So we're going to need to figure out, what's the coordinate pair if I'm on the positive x-axis? Well, no matter what, I know that my radius is equal to 1 because I'm on the unit circle. Now for this one, if I started at my origin and I went out to the right, I would move a distance of 1 because that's the radius. But that's also representing how far I moved on the x-axis. So my x value here is going to be positive 1. And my y value, well, I didn't move up or down, so my y value this time is going to be 0. This is kind of flipped of before, because before we were on the y-axis. So when I'm on the y-axis, my x is 0 and my y is going to have a value. But if I'm on the x-axis, my x will get a value and my y will be 0. Why don't you guys pause the video right now and find sine, cosine, and tangent of 360 degrees, and then we'll check it. Okay, let's start with sine. So if we start with sine of 360, sine is opposite over hypotenuse, or if we look at the alternative definitions up here, sine is y over r. Our y value here is 0, so it's going to be 0 over, remember our radius is always equal to 1. So 0 over 1, I'm allowed to do that, that's okay. So 0 over 1 is just going to be equal to 0. So sine of 360 is equal to 0 then. Let's do cosine now. So cosine of 360, remember cosine is adjacent over hypotenuse, or x over r. So the x value now is 1. over my radius, remember, is always 1. So 1 over 1 is just going to give me positive 1 then. Our last one to do is tangent of 360. Remember, tangent is opposite over adjacent, or y over x. So tangent of 360 will be a y value of 0 over an x value of 1. And this is okay because the 0 is on top. 0 divided by 1 is 0. So although before in example 8 we got a tangent value that's undefined, that doesn't always happen on the axis. It really depends on what this ratio is on this y over x. Okay? One thing I want to point out for you guys is we were talking about negative angles as we went around. And there's actually a pattern that goes with those, and I'm wondering if you've noticed it. So depending on the quadrant, I could tell you which trig values are going to be negative. I know that in which trig values will be positive. I know in quadrant 1 that all of them are going to be positive. So I'm going to write an A there, and what that A stands for is that all trig values are positive. Okay? In quadrant 2, I know that only sine is positive. So I'm going to put an S there to mean that only sine of an angle is positive. In quadrant 3, I'm going to put a T there, and that means that only tangent is positive. And our last one is going to get a C because only cosine is positive, not all, only. So in quadrant 4, only cosine of an angle is positive. What this is helpful for is remembering as you're going around to make sure you're labeling sides that are negative if you go to the left or if you go down. And a good way to check this is at the end, if you're looking at an angle in quadrant 1, then all 3 of your answers for sine, cosine, and tangent should all be positive. If your angle's in quadrant 2, then when you look at your final answers, sine should be the only answer that's positive, cosine and tangent should be negative. And in quadrant 3, only tangent is positive, which means sine and cosine will have negative values. And in quadrant 4, only cosine should be positive, so sine and tangent should give you negative values. Now, we have an acronym to help us remember this ASTC, and that phrase is all students take calculus. So A, S, the T, and then the C. And remember, this stands for which ones are positive in each quadrant. And if you go back and you scroll up and you look at all the examples you did, you're going to see that this is following this pattern, which is just another way to help you kind of check your answers at the end of these. Okay, that is our end of learning target 13A.